So I hope my screen is visible.
Yes, sir.
Uh,
Visible, sir.
yeah, thank you. Yeah, so we will get started. So if we recollect, this is where we stopped in the previous week, right? So we asked ourselves the question, what happens, if we have a control design problem and you and I end up with a closed loop characteristic polynomial, and we need to figure out the controller parameters, which would stabilize the closed loop system, right? So we identified that the problem in general boils down to considering an nth order polynomial of this form. And the question arises, how can one determine the distribution of the roots of this polynomial? Okay. So because for closed loop stability, we need all the closed loop poles in the left of complex plane. Okay. That's where we are, right? So this is the question which we pose. This is where we stop. So let's continue from here. So the baseline problem is that, like, we have this nth order polynomial, right? D of s, which is a naught s power n, a1 s power n minus 1, all the way till an minus 1 s plus an. The question becomes, when is it Hurwitz? That is, all the roots should be the left of complex plane. So the first condition that you and I need to check is that all the coefficients of this polynomial should be non-zero and of the same sign. Okay, so there are coefficients a0, a1, a2, all the way to an, right? All of them should be non-zero and of the same sign. Okay, so this is a necessary condition for the polynomial to be Hurwitz. So what does a necessary condition mean? Necessary condition means that if it's not satisfied, it's not Hurwitz. Okay, so that is why we will come back later. We would have written this statement for the previous problem. Okay, we will return back to this later on. In this closed loop characteristic polynomial, the coefficient of s squared is 0. So certainly, PI controller will not work in this example because there is no way for any value of Kp and Ki, we will be able to place all the three closed loop poles in the left of complex plane. Okay. So anyway, we will return to this, but I have preemptively given you the answer, right? Based on this necessary condition. So, but the necessary condition is not enough. So what do I mean by that? Let's say we have a polynomial where all the coefficients are non-zero on the same sign. Same sign means, all the coefficients should be positive or all the coefficients should be negative. Okay, so that's what it is. If the necessary condition is satisfied, then we construct what is called as a Routh's array. So how do we construct the Routh's array? It is this. Okay, so we write the powers of s power n minus 1 all the way till s0. Okay, so whatever is the highest power we write. Okay, if it's s cube, we write s cube, s squared, s power 1, s power 0. Okay, as the first column. Then you and I only will take the first two rows of this array, that is the s power n and s power n minus 1 row, and then we write the coefficients of this polynomial in a sequence. So we write a0, a1, a2, a3, a4, a5, how many ever coefficients. Okay, so that is the first step. Then what we do is that, like, we go to the s power n minus 2 row, which is the third row. Then we start calculating the coefficient b1, b2, b3 and all. How do we do that? Okay, so there is a pattern to this. B1 is calculated using this formula. Okay, it's easy to remember. It is the product of A1 and A2. You diagonally multiply them and then subtract the product of A0 and A3 and then divide by this pivot A1. Okay, so that is B1. Now to figure out B2, which is this entry, we shift one column to the right. So we multiply A1 and A4, subtract the product of A0 and A5, and then divide by A1. So like this, we complete the s power n minus 2 row. Then we come down one row further, which is the s power n minus 3 row. For this, we take the two rows immediately above it. So we fill in the entries C1, C2, C3 and all. How many ever entries are there? Okay. So for this also, we use a similar logic. Okay, so for C1, We multiply B1 and A3, subtract the product of A1 and B2 and divide now by B1. For C2, we shift one row to the right. We multiply B1 and A5, subtract the product of A1 and B3 and divide by B1 once again. Okay. So like this, we keep on filling the routes array. And then, like what happens is that like we get the first column of the routes array. So once we get the first column of the routes array, the necessary and sufficient condition for this polynomial to be Hurwitz is that there should be no sign change in the first column of the routes array. What do we mean by that? That means if we look at the first column of the routes array, it is essentially, you will have, if there are no sign changes, then, the polynomial D of S is going to be Hurwitz. Okay, otherwise it is not. Okay, so that is the bottom line. All right. So, so the point is, we construct the routes array. Okay, we essentially go through the steps of constructing the routes array, and then like we look at the first column, there should be zero sign changes. Then the polynomial is Hurwitz. All right. Okay, that's what is called as the routes criteria. Now, a corollary of that is that, like, what is a corollary? A corollary is a result which follows from a previous result. Okay? So the corollary of that is that the number of sign changes, if at all there are sign changes, we know that it's not Hurwitz. So what do we mean by that? Of course, there are going to be roots in the right of complex. Okay, not all roots are going to be in the left of complex. So the number of sign changes in the first column of the routes array is equal to the number of roots of D of S in the RHP or right of P. Okay, so that is the corollary. So what do we do now? So we take, let's say we understand through two examples. Let's say we take two polynomials D1 and D2. Okay, third order polynomials. Okay, and D1 is S cubed plus S squared plus 2S plus 1. D2 is S cubed plus S squared plus S plus 2. So what is the only change between D1 and D2 that we can observe?
Coefficient swapped, sir. Of S and
yeah, the coefficient of S and the constant term are swapped. Okay, that's all there is to it. Okay, so essentially, the coefficients are of S and the constant term are swapped, and consequently, what will happen is that you can we can see that what is the impact of that, right? At first glance, it looks very simple, right? So now what do we do? Let me redo the same example here. So as per the routes criteria, first we check the necessary condition. Is the necessary condition satisfied here?
Yes, sir, because all the coefficients are positive.
All the coefficients are non-zero and of the same sign. So you can see that for D1, the coefficients are 1, 1, 2, and 1. For D2, they are 1, 1, 1, and 2, right? So the necessary condition is satisfied. Okay. So this is the necessary condition. Now, it is, we look at the sufficient condition. For sufficient condition, you and I needs to construct the routes array. Okay. So for the routes array, what we do is that we write down, since it is a third order polynomial, we write S cube, S squared, S power 1, S power 0. We take the first two rows. We fill in the coefficients, right? 1, 1, 2, and 1. Okay, so those are the coefficients of the first of the polynomial D1. Then we go to the S power 1 row. What we do is that we multiply 1 and 2, which is 2, subtract the product of 1 and 1, which is 1. So the difference is 1, and divide by 1. So the answer is 1. Okay, so this is a simple example. Okay, so if we go one element to the right, so the question becomes, what happens here? Here to the right, there is nothing, right? So we stop here. Okay, so we keep on filling as long as there are elements. Okay, so once we run out of elements, we stop. So then we go to the S power 0 row. For that, we multiply the product of 1 and 1, subtract the product of 1 and nothing. Okay, so if there is nothing, we take 0 as default. Then we divide by 1. So the answer becomes 1. So here we get a very simple, straightforward example, right? And then we look at the first column. What can we observe from the first column? Are there any sign changes? No, right? So the sufficient condition is also satisfied. So there are no sign changes. So all three roots of D1 office lie in the left half. Okay, so this is the first result. Okay, so now the second polynomial, if you look at it, once again we construct S cube, S square, S power 1, S power 0. Okay, we fill in the elements 1, 1, 1 and 2. So we go to the S power 1 row. So we multiply the product of 1 and 1, subtract the product of 1 and 2, we get minus 1, right? So minus 1 divided by 1 becomes minus 1. Then we go to the S power 0 row, we multiply minus 1 with 2, subtract the product of 1 and nothing, divide by minus 1, we get 2. We get plus 2, because why? Minus 2 divided by minus 1 becomes plus 2. Now, if we look at the first column of the rows array, how many sign changes are there? There are 2 sign changes. How come? Because we start from 1 and then S squared there is plus 1. Then from 1 to minus 1, there is 1 sign change. Then from minus 1 to 2, there is another sign change, right? So we can immediately observe that there are 2 sign changes. So that means 2 roots of D2 office lie in the lie in the right of complex. Okay, so we can see the application of the roads. Okay, I think someone's microphone is unmuted. Any questions? Oh, okay, all right.
I'm sorry,
So-
sir. I'm sorry, sir.
Oh, okay. Thank you. So this is what happens, right? So with the roads criteria, right? Now, let us say this is the closed loop characteristic polynomial of closed loop system 1, and this is the closed loop characteristic polynomial of system 2. So how do we apply Rhodes criteria to our course, right? That's what we are doing. Okay, so if this is the closed loop characteristic polynomial of system 1, then this is stable, right? Because all 3 roots are in the left of complex plane. But D2, if D2 is the closed loop characteristic polynomial of system 2, then the system is unstable. Okay, so that is the implication. Okay, so that's how we use the Rhodes criteria for stability analysis, right? So in our course, that is, we look at the distribution of roots, and if we only if there are the Rhodes criteria are satisfied, the corresponding closed loop characteristic polynomial will be Hurwitz, and the closed loop system will be stable. Okay, if not, it's unstable.
So, Professor sir, for this, the statement that we have written is like the number of sign changes in the first column will indicate that how many roots are lying in the RSP.
Ah.
So if we want to just, what I understand in algebraically, that means some curve which is representing the function that will cross the x-axis twice, right, sir? If I'm not wrong.
So the point is, Roshan, here there is no trace. Okay, it is just that, you know, we have fixed coefficients, and essentially what happens is that, please remember, S is a complex variable. Okay, it's not a real variable. Okay, so you know, like so the bottom line is that, like, there is no trace with respect to a parameter variation. It is just that the value of the polynomial becomes 0 at particular values of S. Okay, so please note, S can be a complex variable. So what you are telling is f of x as a function, right, with x being a real parameter. Then if you plot f of x as x, what you're telling is that, like, look, if x is a real number, you know, like for f1, I will have 3 times it will cut the 0 value in the negative real axis, right? Because all 3 roots are at the left of negative axis of x. But for the second case, you know, like, once it will cut in the negative thing, and twice it will cut in the positive real axis, right? That is provided the roots are always real. But please note, S is not a real number, right? It's a complex number. I hope I have answered your question, right? If
Thank you so much, sir. Thank
the
you so
roots are real, if you are dealing with real polynomials, what you have told is correct, right? So in essence, what it means is that, like, now we go to a three-dimensional representation where you also need to plot the real part and the imaginary part. Okay, and f of x becomes a surface, right? Yeah. Okay.
Right, sir. Thank you, sir. Got it, sir. Thank you.
All right. Okay. So this is another note for polynomials till order 2. That means till n equals 2, the necessary condition is also sufficient. That is, what is the necessary condition? All coefficients being non-zero and of the same sign. But as we observed in the previous example, for polynomials of order 3 and higher, the necessary condition, if it's satisfied, doesn't mean the polynomial is Hurwitz. Okay, so sufficient condition is different. So we can easily show it. If we consider a first order polynomial, if we say d of s is a naught s plus a1, it has only one root, right? So s, the root is going to be minus a1 by a0. So consequently, we can observe that if both all coefficients are non-zero and of the same sign. See here, all coefficients mean only a0 and a1. If both are non-zero and of the same sign, s is going to be a negative real number. So you can see the necessary condition is also sufficient. And if you have a quadratic polynomial, a naught s square plus a1 s plus a2, if you construct the root array, in the first column, we will get a naught a1 a2. That's it, right? So given that, like from the necessary condition, if there are no sign changes, a naught a1 a2 is going to be positive under the same sign. And so essentially, we are going to have the necessary condition to also be sufficient in this particular case. Okay, so that is the difference. That is the unique aspect for polynomials of order 1 and 2. All right. Okay. So any questions on the Routs criteria before we go back to the control design example? All right. Okay. So now let's apply and then apply for our course, right? So now we go back to this example, right? So if you recollect, what was the example that we are considering? We are considering this plant, right? 1 by s squared minus 1, which is an unstable system. We were trying to design a negative feedback closed loop control system for this system. We figured out that the proportional controller does not work. And then like we went to PI. For the PI controller, this was the closed loop characteristic equation. So we could observe that this is a third order equation with two parameters Kp and Ki. Now if we apply the Routs criteria, we can observe that s cube is plus 1, but there is no s square term. So the coefficient of s square is 0. So consequently, the necessary condition is violated. So we can straight away, you and I don't even need to construct the Routs array. The necessary condition is not satisfied, the polynomial is not Hurwitz. So if this closed loop characteristic polynomial is not Hurwitz, then there's no way this closed loop system is going to be stable for any value of Kp and Ki. So that is why we can immediately write that PI system will not stabilize this particular closed loop system. Okay, so I hope this conclusion is clear. All right. So as we discussed, we try P, then we try PI, then we try PD, then we try PID, right? So let's try with a PD controller. Okay, so that's what you and I are doing now. So we come back to this example. We recall that the plant transfer function is 1 by s squared minus 1. So for PD controller, the controller transfer function is KDS plus KP, right? So the steps are the same. So once we start doing these problems, you and I are going to become very familiar with these steps, right? So the feedback path transfer function is C of s times P of s, which is KDS plus KP divided by s squared minus 1. The closed loop transfer function is going to be G of s divided by 1 plus G of s H of s. So H of s is 1. So because since we have unity feedback, so G of s is KDS plus KP divided by s squared minus 1. And then 1 divided by 1 plus KDS plus KP divided by s squared minus 1. We simplify this. Then we get this as the closed loop characteristic transfer function. Sorry, closed loop transfer function. So the closed loop characteristic equation is denominator polynomial, which is the closed loop characteristic polynomial being equal to 0, right? So which becomes this. Now, what is the order of this closed loop characteristic polynomial? It is 2. So as we know, as we just observed, for polynomials till order 2, the necessary condition is also sufficient. What is the necessary condition? No coefficient, all coefficients must be non-zero and of the same sign. Here there are three coefficients, right? S squared, an nth order polynomial will have n plus 1 coefficients. Okay. So there are three coefficients for the second order polynomial. There's a coefficient for S squared, there's a coefficient for S, there's a constant term. What is the coefficient for S squared?
It's positive, sir. 1.
It is plus 1, right? So the condition for the closed loop polynomial, closed loop characteristic polynomial to be Hurwitz, or in other words, the closed loop poles to be in the left of complex plane, which will imply that the closed loop system will be stable, is that the two remaining coefficients must also be non-zero and of the same sign. So what does it mean? KD should be greater than 0 and KP minus 1 should be greater than 0. I hope it's clear how we got these two conditions, right? Once again, for polynomials till order 2, all the coefficients must be non-zero and of the same sign. That is the necessary and sufficient condition for the polynomial to be Hurwitz. Essentially, what happens is that, like, in this case, since the coefficient of S squared is plus 1, the remaining two coefficients also should be positive. So KD is greater than 0 and KP minus 1 is greater than 0. So if we simplify this, a PD controller will stabilize it as long as KP is greater than 1 and KD is greater than 0. Okay. So this is the graphical representation of the controller parameter space. How do we get this? Let me illustrate it. So as we remember, controller parameter space means we plot the range of controller parameters that will stabilize the closed loop system. So if we plot KP and KD axis, KD greater than 0 is this half plane. Okay, so whatever is above the horizontal axis is KD greater than 0. KP greater than 1 means we draw a vertical line at 1 and all points to the right of this line is KP greater than 1. So now you and I are looking at the feasible region, which is the intersection of the two conditions, right? KP greater than 1 and KD greater than 0, which is this, which is the intersection of the two feasible. Okay, so this is the feasible region for stability, for closed loop stability. So this is how we solve this problem. However, one may immediately ask the question, hey, what have we done? Is this beneficial, right? It's a very natural question to ask. So essentially, one may say that, hey, look, at the beginning, you had KP and KD to be infinite dimensional space, right? So then, and then we have converged it to something in the first quadrant, okay, of this controller parameter space, but still it is infinite, right? So it's a if you can, if I can broadly use a term, it is less infinite than before, but still it's an infinite region, right? So, but we have narrowed down, okay? So the main advantage of this analysis still now is that you and I will not choose, let's say, KP, KD here or here or here, because through this example, through this analysis, we know that if I choose KP and KD in the remaining quadrants, I am assured of instability. And for that matter, here also, in this region, okay, let's say at this point. So you and I can prevent instability. But then, how do I choose KP and KD now to get a particular value which I can program into an onboard controller? So that's where performance specification comes. And this is also related to the question that was raised in the previous class, right? So in the previous class, we talked about derivative time, integral time, and so on, right? So when there are two parameters, KP and KD, based on certain constraints, we also try to fix the ratio, okay, which physically come in the form of integral time and derivative time. So that ultimately the problem boils down to varying one controller parameter, okay, for performance. And you and I will learn tools, what is called as root locators and so on later on, which will help us, right? Come up with the best possible sub ranges, okay, in this larger range for KP and KL, okay, as we go along. Okay, so that is this example. So I'm going to leave you with a question. This is not a homework. You please figure it out. This once again, this will be answered in my control systems course. So you can watch the NPTEL videos that I have already shared, right? So in that, the answer for this will be found. But then yeah, I'm just giving it as an exercise, self-learning exercise, so that you and I can continue with our course, right? So let's say there is a element in the first column of the roads array, right? Let's say it becomes 0 due to whatever reason. What happens with the particular calculation? Let's say, for example, we have a polynomial which is this s cube plus s squared plus s plus 1. So what will happen? This necessary condition is satisfied. If we construct the roads array, we are going to get 1, 1, 1, and 1. Now, what will happen in the s power 1 row? We multiply 1 and 1. We subtract the product of 1 and 1 and divide by 1. What will you and I get? We will get 0. Right? Now, we go to the s power 0 row. We multiply 0 with 1. Subtract the product of 1 and nothing. We divide by 0. We get 0 by 0. So, what do we fill here? It becomes undefined. So, I hope this condition is clear, right? So we may always get these special conditions. So those will be answered in that NPTEL video. Kindly watch it, right? So I will also discuss what is the physical implication as far as closed loop poles are concerned. For you and me, for automotive control, we are very clear. We want all poles to be the left of complex plane. So you and I will design only those controllers which will ensure that all the coefficients in the first column of the roads array are non-zero and on the same side. That's it. All right. So this is what we would have learned in this particular video. So once again, I'm sorry that I was late, but I think we have just enough time for a few questions, maybe, right? Before your next class starts. Any questions? Yes, please.
Sir, am I audible?
Yes, please go ahead.
Sir, Prem here. Just one question. Actually, a couple of questions, but in interest of time, I'll ask only one question.
Okay.
The graph that you have displayed on the right-hand side, the KP versus KD, it so happens that I'm able to see KD value when it is greater than 0, no problem. But the LHP plane on the bottom side is also possible, meaning KD less than 0. I'm not really able to visualize KD less than 0 happening.
Okay. Prem, this is not the complex line for us to understand. Okay, this is a controller parameter space. Okay, this is not the S plane. Okay, point number 1. All right, and see, how did we get these? See, this is only a graphical representation of the solution. That's all there is to it. Okay, we have not done anything more. So, if for this closed loop system to be stable, we need both these coefficients to be greater than 0. I hope that's clear to you, right?
Yeah, sir, that is clear. Just the fact that as a negative value, I'm not able to visualize.
No, negative value means it's unstable. So only the hashed region is stable. Okay. So
essentially, we'll not be able to have that value at all in any one of the cases where stability is required. That's all, right?
Absolutely not. Right. See, in this diagram, whichever region I'm shading in red, it is not feasible. Okay, only the thing which is shaded in purple or blue, right, or magenta, right? That is the feasible region. Okay.
And typically, in most controller design, we will not be able to see this happening on the left-hand side, correct? That's
no, not really, Prem.
Yes. Okay.
Use left-hand side or right-hand side here. Okay, that is why I clarify. See, left of plane, right of plane are okay to me for as far as this particular course is concerned. In this context, right? Let me be very careful, right? I would use only for the complex plane, which is the S plane. Here, you and I are plotting real valued parameters. Okay, so that's why I use the term quadrants rather than half plane, right? Left off and right off. If you notice the terms that I used, right? So.
Understood, sir. Just wanted to understand whether that negative value alone.
Yeah, absolutely. It may be possible. You never know. See, for example, let us say for the sake of argument, let us say something, we have another system where the closed loop characteristic equation of the PD controller comes like this. So what do we have for stability? We want minus KD to be greater than 0, KP minus 1 to be greater than 0. Then KD should be less than 0 and KP should be greater than 1. That will be the feasible reader. Then it
Yes,
will
sir,
exactly the other way around, right? Yeah. Okay. So you never know, it all depends on the system that you and I are given.
Okay, understood. Okay. And maybe, sir, just an attempt at the question that you have asked. So, what happens if the first column in a row of the rows array is 0? System will definitely be unstable only. Am I right?
So that is a tricky point, right? So if only the first entry is 0, you will have what are called radially opposite roots on the imaginary axis. And if there is no other sign change, you will have close to pole or the roots on the imaginary axis, but no roots in the right of plane. However, if you have sign changes in the first column, you will have radially opposite roots. What do I mean by radially opposite roots? Let's say if we have the S plane, this is the imaginary axis, sorry about that, right? So now I'm looking at the complex plane. So if you have a root at +2 and if you have a root at -2, they are called radially opposite roots. Why? Because they are equidistant from the origin 180 degrees apart, right? Is it not? Similarly, if you have a root at +3j, -3j, that's another case of radially opposite root. Okay. Then you can have these 4 roots that forms a set of radially opposite roots. 1, 2, 3, 4. Because you can draw a circle through the center of the origin. So you can have all these cases of radially opposite roots. Okay. So when the first term happens to be 0, you will have radially opposite roots. Whether you will have roots on the right of plane or not depends on whether there are other sign changes in the first column. But anyway, from a control design perspective, why did I not teach those subtle points to us here in this course? As I mentioned, in automotive control, you and I want closed loop system to be stable, right? You and I don't want closed loop poles on the imaginary axis. So if some controller will give me a 0 entry in the first column of the road, say I will discard that controller because there is no way I can stabilize the system, right? Even if I have poles on the closed loop poles on the imaginary axis, it's not of much use to me, right? Is it not, Prem? Okay.
Yeah, sir, that's why
I didn't go into the control theory. Okay. But you can find it in the lecture video, right? So, okay.
Noted, sir. Thank you. Just maybe tomorrow when we are discussing, you can just illustrate the example when it is becoming 0. Just
yeah, exactly, right? This example which I illustrated. So if you calculate the roots, you will see that. Why don't you calculate the roots and tell me tomorrow, right? Of S cube plus S squared plus S plus 1, you will find that there will be 2 roots on the imaginary axis. That's it. We already solved, right? Fine. All right.
Thank you, sir.
Okay. Yeah, welcome. I think it's already 6. I'm sorry once again for being late. Arunachalam, is everyone present today? No.
Sir, everyone present, sir.
Okay, then I'll mark attendance for everyone. We will continue tomorrow. Hopefully, I should join on time. But once again, there is a big delegation coming to the department at 4 p.m. So once again, since I am also doubling up as head of the department, I am pulled into all these official meetings. So kindly wait if I'm late by a few minutes. Okay, I'm very sorry.
No
issues.
We will wait.
Yeah. We will meet tomorrow, please. Okay, thank you.
Yeah. Thank you, sir.
Thank you.